Now it is visible, right?
Yes, now visible.
Oh, oh, aesthetic. Okay. So we have to make maximization of this omega, right? So we had lots of distribution. Last class we discussed. Among those distribution, you see here, one distribution will be highly probable compared to other. That highly probable distribution we have to find out. Okay. So how we can do that? You have to make derivative, correct? So just remember, this was our this, what does it mean? It is a number of ways of a particular distribution, correct? Last class we discussed in detail. So this is a distribution, and this is the number of ways by which you can get those distribution, correct? Is it clear?
Yes.
And what was its formula? If you remember, it is total number of microstate a factorial divided by this. Okay. Now
Yes.
there are. I'm assuming there are lots of distribution, correct? Lots of distributions are there. So I'm assuming another distribution, that is this a instead of a j. It I'm using a k, just a dummy variable. For a k it will be just a
AK
k.
factorial.
A k factorial, correct. So now what we have to do, we have to just maximize this omega. From that maximization condition, we can evaluate the most probable distribution. That's our case, because we have already discussed in last class. We plotted omega over the distribution. So we saw that for a particular distribution that is highly probable, and rest of the distribution, the probability of rest of the distribution compared to that most probable distribution is negligible, or you can consider zero. Correct? So
Yes.
we will do that. Just follow it. If you have any doubt, you can ask. So it is ln
Okay.
omega. I'm not carrying this part. Okay. You have to just keep in mind that that functional part is there. Okay. Argument part is there. So it will be ln a factorial minus ln. Okay. Ln a factorial. If you take this multiplication out of this log, then it will be summation. Okay. So this is our ln omega. Now,
Can we use Starling approximation?
yes, we have to use the Starling approximation. Where we will use the Starling approximation? In both cases, we can use, because this for the what is the Starling approximation? Starling approximation, that is ln x factorial can be written down as x ln x
X ln x minus x.
minus x. But this Starling approximation is a good approximation for a large value of x, correct? It's not true for small
Yes.
value. Let's say if it is ln 2 factorial, x is 2, then ln 2 factorial equals to 2 ln 2 minus 2. So this is not a good approximation. Let me just put ln 2 factorial. Ln 2 factorial is 2, so ln 2 is this side is 0.9693, and this side is 2 in ln
2 into 0.693 minus 1.
yes. So it is ln 2 into 2 minus 2. So you see it is, here it is minus 0.613. So value is not matching. So it's not a good approximation here. For small value of values of x, it's not a good approximation. But let's say if it's a 20 factorial, then you can write it 20 ln 20 minus 20. Okay. So what does it mean then? Ln, okay, 20 factorial is a huge number. 20 factorial calculator. Where is the factorial sign? Here. This. Okay, ln of n. So it is 42.33.
Ln 20 is 1.693.
And right hand side,
20 into 1.693 minus 1.
minus 20. Yes. So it is giving 39.91. So see, that now it's getting closer.
Yes.
Correct. So when it is 100 factorial, then you will see that it's more or less same. So for a large value of x, it is a good approximation, standing approximation. Now you remember this capital A is a huge number. This number of microsecond is tends to infinite.
Yes, it's infinite.
It is infinite, tends to infinite. So we can easily apply standing approximation. And in this AK part, this is also huge number. What does AK means? AK means the energy level with the number of energy level with the energy K, EK, right?
Yes.
That is also a huge number. If capital E is let's say 10 to the power 23, then for particular energy level there must be 1000, 10,000 level should be. So it is also a huge number.
Yes.
You can safely apply this starting approach here because it actually uh, strengthen our approximation that ergodic hypothesis. If you remember, if the number of replicas is very, very high, then it will be more prominent, correct? It will be more appropriate to use ensemble average
Yes.
instead of in the place
Equals
of
to time average.
time average. So that's why it's okay. So it's actually in the same side. So you can use, so then ln omega will be just replace, it will be a ln a minus a minus sum over k ln here a ln ak minus ak. Okay, no, this is ln ak factorial, so like that. Oh, okay, sorry, so this will be just ak ln ak minus ak, correct? Write it. Is it clear now? Now if you remember, we had two constraints. These two constants are there. We have to keep in mind that we are maximizing, but keeping in mind there are two constraints. One is this, another one is
Summation AJ.
yes, because overall energy is not changing because it is in a
Yes.
thermal bath. So, so you can write this value. What is this value? This is actually total A, correct?
Capital A.
Capital A. So this will cancel. This will cancel. So you can write till now we are not maximizing. We are just simplifying the expression for the omega. Now, instead of maximizing omega, we will maximize ln omega. The same thing, nothing will change. When, let's say you have a function y is the function of x, then if you want to find out the maximum point of the y, then how you can do that? You have to differentiate, right?
Calculating the dy dx.
dy dx from dy dx equal to 0, that will give you maximum or minimum point. Correct. Then
Yes.
after doing second derivative, you can uh, confirm whether it is a maxima or minima. But instead of y,
Yes.
you can maximize the ln y as well. Take ln y and take the derivative with respect to x. Then also it will give the same answer because position will not change, correct? ln y, if when you do it, do
Yes.
d ln y dx, what does it mean? You can write it d ln y dy and dy dx. So this is 1 by y dy dx. So ultimately you are doing this one. Okay. Just ln
Yes.
y does not add some new flavor. But why we will use that? Because the equation will be simplified. Otherwise, the
Yes.
equation will be looking more complicated. That's the reason. That's why we are doing here. We are maximizing considering ln, not the direct omega, just the ln omega. That's the thing. So here we will introduce the Lagrange multiplier. Okay. So what should we do? We have to do this for maximizing. If we want to find out any maximum or minimum of a function, we have to do this. Correct? This you know.
Yes.
So here also we will do that. So here it will be d of the aj. Correct? This we have to do.
Yes.
But here two constants are there that we have to keep. So that's why it is not equals to it is we have to mul- subtract that part as well, not just ln omega. Instead of ln omega, we have to do sum over k a k. This was capital A. This is one constant. Another constant is a k e k. This we have to do. Okay.
Why we did this?
Uh, this is called Lagrange multiplier method. So when you have constraint, then you have to do. Okay. In detail,
We
you
have
have
to
to do.
subtract it from the part.
Yes, yes, yes. Let's say you have a function y is a function of x. And now you want to find out the maximum point of y. Then in general you do dy dx equal to 0. But let's say I'm giving a condition that let's say y minus x should be 2, something like that. Some condition, or y is greater than 5. That is another condition. If you have that kind of condition, then you have to use this method. Okay. Any condition if you
Then
have,
always we will subtract the condition.
hmm, yes, that you have to do. But it's clear that it is we are taking derivative, correct? So taking this one constant, or it's better to take this one. Alpha and beta, these are two constant. This is more general form. Okay.
Lagrange undetermined multiplier.
Yes. And this method is called Lagrange multiplier method or undetermined multiplier method. So and these are the called Lagrangian multiplier method constant, like alpha beta constant. If there are three constraints, then we have to subtract three. Okay. So these alpha and beta are the
Here are
constant.
two constants.
Two constant. So this we have to do. One more thing, you see here we have taken this uh, omega. This is function of ak. This is ak. This is ak ek. But we are differentiating with respect to aj. Can you guess why? These are the dummy variable, right?
Yes.
Then why we are doing that? Instead of AK, we are differentiating with respect to AJ. What is the motive to do that?
Can also differentiate with respect to AK.
Can.
Differentiate with respect to AK.
We can do.
Yes.
Sure. No, actually. Why? Okay. Let me take an example. Just have to think 1 minute. Okay. Let's say y is equal to sum over xi. I equal to 1 to 2. Okay. What will be y
Yes.
square?
3.
3 means
Sorry, y square is 9.
how?
Sorry,
No,
x1 plus x2 whole square.
I want to have the general formula, not the numerical one. I is 1 to 2, not xi is 1 to 2. It is x1 plus x2. Why?
Yes, x1 plus x2 whole square.
What will be the general formula? Can I write this?
No, sum over xi whole square.
Sum over xi whole square. This.
Yes.
Okay. This one, correct?
Yes.
So why we can write xi square? So in general,
Because
how you
there is
can
an
write it?
extra term.
In general, how you can write it? Or let's say, okay. Now let's say I will differentiate with dy. I will differentiate with now x1 or any of the any x I want to differentiate. Then how we can do? What will be the answer? Or for better your understanding, let me do it exercise plus. What will be this derivative?
2xi.
So it is sum over this one, correct?
Yes.
Now let me check. Let us check. So y is our x1 square plus.
x2 square.
Now we are this formula. If this formula is correct, that means if it is x1, so it is okay. Sum over I will be there, correct? Okay, 1 to 2. Actually, no sum over I will be there. I'm writing so 2x1 plus 2x2.
Yes. But this will result different.
Let me check. So this is this.
2x1 plus 2x2 dx2 dx1.
No, these are orthogonal. Let us consider. Okay, or if you want to keep it, so this value is not matching, right? These things are not matching.
Yes.
Now just take that derivative dy dxk. Just using another notation, have xi and xk are the same thing, just dummy variable. Then it will be d dxk sum over I xi square. So it is sum over I dxi square dxk. So it is sum over I 2xi dxi dxk.
dxk.
Now you just open it. It
Yes.
will be 2x1. Then, oh, okay, we are doing dy dx1, correct? So it will be now 2xi dxi dx1, so it is 2x1, dx1 cancel, 2x2, dx2 dx1. So it's matching.
Yes.
So why we have to take another variable? Because to consider the cross term, that's the reason. If you take both the same xi, that essentially actually you are neglecting this cross term. It is x2, it's not the same thing.
Okay.
Here you will treat both as xi, that's why you got this answer. You are considering both term as the same term. That you can't do. So take the cross term, account the cross term, we have to consider this a dummy variable. That's the reason. Now get it? This example, from this example, I
Yes.
think it is clear why you have to take the different notation. So that's why you have to
Yes.
consider aj. But this aj and ak are the same thing, just dummy variable, nothing. This error is occurring due to the just due to notation. Nothing is there. It is just a error
Yes.
due to notation. So to avoid this error, we have to consider the different notation, which is called the dummy variable. So later on, we'll see various usage of dummy variable. Okay. So now we'll proceed.
Yes.
So we have to do this derivation, differentiation. So we'll do term by term, right? Take the first term only. So it is this one. Now ln omega we have already derived form of ln omega. This is the form of ln omega, correct?
Yes.
So we'll put that. Today's class is not that much difficult because last class was more conceptual. That was derivation is not difficult thing. Understanding the concept part is more difficult.
Yes.
This is mathematics. Mathematics is always easy. Okay. So first term, this capital A, this is a total number of microstate. This is not a variable. This is
This is
constant for
constant.
each and every distribution, correct?
Yes.
So this is 0. And the second part, that is interesting. There are two terms. Okay, one thing you notice, what I did, this little things you have to notice. Summation was after derivation, but I just exchanged the order,
Can we do
correct?
this?
Can I do that?
No,
No, why?
because it is sum over k and this is
Let me
del
take
del
sum
aj.
over. Okay, let's say k is 1 to 2. It is ak ln k. So it is actually a1 ln a1 plus a2 ln a2. And you are taking the derivative with respect to del a1. Let's say j is 1. So we have to do this. So this means it is del a1 ln a1 plus a2 ln a2.
Yes.
So it is del a1 ln a1 plus del a1 a2 ln a2. Sum over k 1 to 2 del a1 a k ln a k. You think it's wrong? Just check it. So can I write?
Yes, you we can write it.
So why, what is the reason? Because you know derivative or differentiation, whatever you want to say, is commutative with addition. Okay, means commutative means
Yes.
order is not important. If you do differentiation first and then add, or you add and then differentiate, it does not make any change. You know. That's why when it is x1 plus
Mm.
x2 and you have to take the derivative, you just break down the derivative, right? That reason is derivative and addition is commutative. Can you give an example where addition is not commutative with that operation?
Square.
Square. Easiest example. In case of square, that is not commutative with addition. Okay. But square is commutative with?
Okay. Multiplication.
Sure. Yes. Okay.
Yes.
So now, so that's why you have do it. Okay. So it is minus sum over k. Sorry, it is aj. Now you know what you have to do. This term is first ak and then 1 by ak plus ln ak. Is it clear?
Yes.
And this part is, what is this part? Can you recognize this part, this term?
The cross term.
Kronecker delta.
Yes. Connector delta kj.
If k equal to j, then it's 1, otherwise it is 0. So you can write it.
Yes.
So clearly, it is 1 plus ln ak delta kj. That means if k equal to j, then only this will survive, otherwise this will be 0. So directly you can write,
Yes. ln aj.
is it clear?
Yes.
Somebody joined, I think, right? So, okay, so this is our first term. And second term we will now do. Second term is this. This is our second term. This we will do. Okay. For second term is del aj. We have to take difference derivative with respect to uh, alpha sum over k ak. So what will be that? Alpha is just a constant, and this is
Yes.
this.
Connector delta kj.
So it is just 1. It is 1 only when k equal to j. Otherwise it is 0. So it will be
Yes.
only 1. This is the second term. And what about the third term? Okay, here also the same thing.
ak into del ak del aj plus ak into del ak del aj.
Now we are we are differentiating with respect to A, right? Not E.
Yes.
So E is actually constant,
Beta
but
ek.
it's not out of summation.
Yes.
Okay. So total, what you can
Why
write,
this summation is getting off?
Kronecker delta, right? It will survive only when k equal to j.
Yes, but for only this connected delta part, k equal to j. But the other part,
It is multiplied, na? So 0 multiply 0 with something, that will be 0.
okay.
So it is ln. So it is what we get. This is equal to 0, and this part, this we get minus 1 plus ln kj, then minus 1, then minus beta
Beta ej.
equals to 0. Now this aj should be our most probable distribution aj star, because we are
Yes.
equating with 0. This is our most probable distribution. So okay, it is okay. Not it is not 1. It's alpha, right? So it is
Yes, it's alpha.
it's alpha. So we can write minus ln aj star minus 1 equals to alpha plus beta ej. Just taking alpha plus beta, and that's right. Okay.
Yes.
Now okay.
Yes.
Okay. That means just so aj will be
2 to the power minus alpha dash plus beta ej.
so you can write it as okay. This is all our aj star. Correct.
Yes.
So this is our most probable distribution. We have find it out. But can we more simplify it? Can we have other expression that we'll see? We know what we know, that sum over j aj star, that is also capital A. It's true for any distribution, right?
Yes.
So it will be e to the power minus alpha prime sum over j e to the power minus beta ej equals to capital A, because here j term is there. This is constant, right? So no j will be there. So it is clear. Can we write it?
Yes.
Okay. So if we can write it, then this is also true. So aj star will be now what we can write. This was our aj star. So it means can we write it?
Yes.
Sure. So we are done. If you remember, we had the expression of average values. This was our expression for average values. We just needed the xj term. So what was our pj? Pj is this. This one our
Yes.
this one our PJ. So just we'll use that. This AJ we have calculated. So PJ or star, whatever you want to write, star, that is AJ star by capital A. This is finding of a microstate with energy level EJ. So that will be just capital A, capital cancel out. So e to the power minus beta
E to
EJ.
the power minus beta ij by sum over e to the power minus beta ij.
It is written as e to the power minus beta EJ divided by Q.
Q.
So this is for Q. Partition function. Or more properly, if you want to write it, then Q is sum over. And if you remember, EJ was function of N and V. From first
Yes.
last time we discussed, if you remember, E was function of N and V, right? So EJ is function of N and V. So Q will be function of N,
N and V
N, V and
and temperature.
beta.
Temperature.
Beta. Same thing. Beta is one by. You
Yes.
don't till now you don't know what is beta. If you remember, beta is just a
1 by
constant.
cavity.
Beta is just a constant for this Lagrangian undetermined multiplier. This is not any temperature. Okay. Till now, this is just beta. So PJ.
But we know the value.
No, we don't know. We will derive. We will evaluate what is that beta means.
Okay.
When we use the statistical mechanical result in to calculate the thermodynamical property, then we will okay, this beta is actually our 1 by kBT. Then we will figure it out. Till now, that is beta is beta, not inverse temperature. So PJ will be e to the power minus beta EJ divided by, correct? So PJ you know. So XJ
Yes.
easy to calculate. XJ was sum over J, XJ, PJ. So sum over J, XJ e to the power minus beta EJ divided by Q. Clear? I think it's clear. Just take an example. Let's
Yes.
take internal energy. So internal energy U, that is average of E, correct? So that
Yes.
EJ,
Ej pj.
PJ. So it is sum over J, EJ e to the power minus beta EJ divided by Q NV beta. Okay, that is the our partition function. Or in some book, you will find it, it is NVE even. It is written as NVE. It does not matter because you know this beta is actually signifying that overall temperature is fixed. Correct? Overall energy is fixed. If you remember, that's why beta came.
Yes.
In the determined multiplier, why does beta came? Because you have to keep the overall energy constant. So that's why you can write it capital E as well. But it's mathematically it's correct to write beta. So this is called not part. Oh, sorry. This is canonical partition function. Okay. So for any parameter, now any thermodynamical property you can calculate. That is our task. That we can calculate right now. Okay. First thing is we have to understand what does this beta means. Okay. Then we will proceed. Till now we don't know what is the beta. Beta is just a constant, Lagrangian constant, something like that. So till now it's clear.
Yes.
Because in last course we have just used this formula. In general, we just use this formula. We don't derive it. We just use this or this formula. This derivation is not very difficult. Just you have to understand that conceptual part, then it is clear. In statistical mechanics, always when you have summation thing in a general expression, just break it down to a small part. Let's say two system, three system are there. Then just do that. You will get the feeling. In last class, that's why we did not these things. These things. Otherwise, it was
Yes.
difficult to understand. It is much more easier, correct? So now we will calculate the various properties that we'll calculate. But first, we will see what does this beta means and what does the thermodynamical laws are. Is because this canonical part, canonical ensemble, I will not. I want to cover everything. I will not leave anything. We have gone through it once. Just do it by your hand. It will be uh, easy. Nothing. Okay. Okay. Now, yes, we can do this part. So, oh, okay. Did you watch these videos?
Yes.
So what is going on?
The fluctuation part, it was taught today that the Cv, heat capacity at
Uh,
constant volume, is fluctuation in internal energy, and Cp is fluctuation in enthalpy.
Enthalpy. Okay. Okay, that we will also do.
I found it little bit tough.
No, 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 we'll do it. Don't worry. We will do it purely in terms of mathematics. Don't worry.
Okay. And also the second tetrad equation was taught, and from that deriving the PV equal to KVT, that is also taught.
So good total equation we discussed last course as well. In this course we will also discuss,
Yes.
but actually I think Bagji sir is showing from PPT, right? That's why it is going so fast.
Yes.
Uh, but okay, this is our tutorial course. We will go according to our pace. I have no hurry to catch him. But it is very important to understand this canonical ensemble, these things. Okay, that's why I want, because this part you will see, it will not generally taught in our in BSc course, and very in few universities it is taught in MSc course as well. MSc special probably there is in this course. So I thought, okay, so it is clear now. Now we'll discuss some first law. First law you remember, I think. So what is our first law? Let me do it.
Del U equal to Q plus W.
If this is your system, then if you provide heat, let's say decrease the amount of heat you are doing, providing, then it can increase the internal energy or it can do some work.
Or work done.
Okay. Or you can, if it is mechanical, then it is just PdV. These things you know. Okay. So now in statistical mechanics, what does it mean? From microscopic point of view, microscopic picture, what does it signify? That you have to understand. That is quite tricky. So let's say, okay, you just remind that canonical ensemble picture. You have this microstate and you have infinite number of copies of this microstate, correct? And this each and every copy is a microstate. That was our picture, canonical ensemble picture. and total and the energy can be exchanged between these microstate. But total energy is fixed. That's why total the temperature is fixed. That is attached with a thermal bath. That was our overall picture. Correct.
Yes.
Now you are giving heat. Now what will happen to macrostate and the microstate? How the microstate will be changed? That is important. How the distribution of microstate will be changed, because under that condition, we have derived the most probable distribution. So what will be changed in the most probable distribution? If you do work done, or if you give some heat, or if you extract some heat, if you extract some work done, then how this distribution will be changed? That is important. That we have to calculate.
If we give heat, the population will excite to upper state.
Repeat it.
If we give heat, the population will
Yes,
excite
yes,
to the higher state.
exactly. So let me write it. So consider the change in energy work done by the system in state J. So basically, if you remember that EJ was function of energy. Now, when work done is happening, then V is changing, correct? So that is
Yes.
same. Here also PdV is there. That is our work done. That you have taken account. So what we can write. So how the internal energy will be changed? That EJ is the energy of the Jth level. That will be changed by EJ dV. Just same. PdV, P times dV. That is a change in the means before it was like this. Let's say this is our EJ level. If the work done is happening, then volume is changing. So that's what, let's say now, or these are the energy level. EJ is now. So EJ is changed, right? The value of energy level, value of the jth energy level, EJ is changed right now. Population is not changing. Population is same. Let's say 3 is there. 2 is, these EJ are not okay. If you just keep in mind, these EJ are not the molecular energy state, and these are not the molecules. These are in my ensembles. Here 2, 3, 3, 1. Let's say something. Here also the distribution will be same, but as you have provided some work done, or the system has done some work done, this value of EJ will be changed. Is it clear?
Yes.
Okay. And that is related to PdV. This P is called pressure. This is analogous to pressure. Pressure for individual level. Pressure of jth level. Okay. So what you can write? How you can determine this? This is just this. But number of particle is fixed. Number of particle is not changing. For any level, number of particle is not changing. Okay. So what you can write? So only work done is there. No heat is exchanged. We are discussing only the work done case. So now what will be this? Volume is change, right? Means DEDB, and E is just NV beta. And if you remember, N is constant, beta is constant. Beta is constant because always temperature is not changing. It's
Yes.
attached with the heat bar, and number of particles is not also changing. Only we are making one of done. So this is actually in shorthand notation. We can write it like this. So we have to calculate it. If you calculate, then you can calculate the pressure. So just let us calculate. So this you know.
Yes.
So Q is also function of V. That will also be in part of this differentiation. Okay. So now it is just a U by V rule that will apply. Okay. So do it term by term. So it will be 1 by Q. Okay. This is clear.
Yes.
So first part. First this one. If you remember, EJ was function of N and V. That's why it is differentiating with respect to V. So first you can take out the summation, you know. So it is EJ and then okay.
Yes.
So this is, so what we can write it as beta. Correct. So if you take common, and if you remember, this was our PJ, right? Delta EJ del V, this is our PJ.
Yes.
So essentially it is minus beta EJ to the power minus beta EJ TJ plus e to the power minus beta EJ PJ. So it is essentially you can take EJ e to the power minus beta EJ common. So then it will be 1 minus beta EJ. So this is our first term. Okay.
Yes.
So what about our second term? Second term is this. second term is this, so it is q by v is okay. So it is q by v we have to calculate, but it is some del del v. Okay, okay, okay. Dq dv. Okay, correct, correct. That we can do. So is j. So second part is just del q del v is there. Correct. This part is just summation. Del q del v we have to calculate. So what is del q del v? This is, so it is essentially, okay, minus.
Yes.
So now we will put those term there, and then we will see what happens. So this will be for from first term. It is this. This part we calculated, but there is uh, 1 by q. So this overall term will be divided by 1 by q. So it is minus j, this term, ej e to the power minus beta ej q 1 minus beta ej. Okay. And second term was this. So it is minus 1 by q square. Then this is there. Plus will be, because minus minus will plus, and then sum over j e to the power j beta ej. Is it correct or not? Okay. From here you can write it.
Yes.
So now it is easy, nothing to do. So we can write it q plus q plus, so beta is there. Okay, beta is also there. Q, and what is sign here? It was, oh, it is not sign, it is just multiplied. So it is j. So you can write it, just q square was there, so we just divided q. So what is
Okay.
this first term? This is just p average.
Yes.
What is second term? EP average.
Yes.
Third term, beta p
P
average,
average.
and it is E average.
Yes.
So this, so totally this is our form, daily del P. This is our total form. So I think it's clear, right? P,
Yes.
then beta EP, and then E times P. So it's better to write as E times P. Okay. Oh, sign issue is there. I think it's minus beta EP is written here. It is minus or plus? Minus is there, right?
Yes.
Just check. Here was mine. It is minus. It is minus, but one minus we are getting from here as well. Okay, no. Okay, there is a minus sign.
Yes.
We did that mistake. That's why. Okay, there is a minus sign. So eventually this minus will also not be there, and here will be a minus. You take common, then it is actually this.
In physics, the work done is PdV only.
No, here system is doing work done. That's why.
Okay.
Okay, so it is beta pj is correct. Okay, just you can check the sign. Sign is clear. So it will be this. Sign part is not that much important. That you can fix. Okay, but form will be this. You can do this, right? But I should check.
Yes.
Let's check. There is a sign mistake. Ah, yes. There is a minus sign. That minus will goes away. But it is plus 1 by q minus. Is correct. So automatically
Minus 1 by q square.
here it is, this minus will not here, this minus will not be there. So eventually this will be minus. Correct. It's correct. Okay.
Yes.
So this is our daily del V when the number of particle and when the temperature is constant. Now, okay, this is correct. What is this? We will have a great equation just to see. Now the second thing, why we are calculating this, we will just understand after a few minutes. What will be del P del beta? P average it is. We calculated N average. No, sorry. Now P average. This I am just calculating. So what will be this? Just do it. So it is sum over J Pj e to the power minus beta Ej by Q. Is it okay?
Yes.
So again, just you have to divide because Q is function of N, V and beta. So it will be Q times del beta sum over J Pj. Easy in derivation, nothing is there, but you have to just you have to be careful. Otherwise, mistake will sign mistake will be there. And here it will be Q square. Okay, so it is first term is 1 by Q, and this derivation, what will be that? Sum over J Pj, then it is minus Ej, then it will be e to the power. No, just that's it. There will be anything beta Ej, right? This is, if you do that derivation in the first term, then any other term will you get?
Del Ej del. No, no. Okay. This will I get.
But one term you will get, that is when the Pj will be integrated. So then this term will also be
Yes.
there. Okay. And the from, yeah, correct. I think it's correct. Just you also do. And from second term, it is 1 by Q square del Q del beta means sum over J uh, del beta of e to the power minus beta Ej. So it is minus Ej e to the power minus beta Ej times minus goes away Pj to the power minus beta Ej. Okay. So it is 1 by q minus pj ej e to the power minus beta ej. Then this is one term and another term p average, yes, p average q square this one. Can you get any other term? No, I think it's correct. Okay, it's correct. Hmm. This term will not be there, I think. Just see, this term will not be there. My pj is not function. Pj is not function of beta, right? Ej was also not function of
Yes.
beta. So how can pj will be function of beta? So first term is this, EP, EP average. This is E average,
E average, P
P
average.
average. So now, if you combine two result, sum up, then del V when n and beta is constant plus del P del beta when n and V are constant, then what you have from first case, it is this minus P average mm, minus P average plus beta EP average minus beta E times P. And from here it is minus beta EP average plus beta E times P average. So what you will get? Just minus P.
Minus P average.
Okay. So we can write what you can write that minus P average is equals to
Del E, del V. Del E average, del V.
okay. Now
Yes.
can you remember the thermodynamic equation of state? One. What was that? Pi T, that was our internal pressure, that was equals to del U del Vt, right? And it was equals to del U del V, oh, uh, del U del Vt, that was equals to T times del P del TV minus P.
P into del V, del TP.
This is right?
Del V, del TP.
Del V del TP,
No, no, sorry. Del P, del TP. Okay.
correct?
Yes.
So from here what you can write? Write minus P equals to del U del Vt minus, why minus is there? Minus would not be there. Oh, minus, tick, tick. Oh, this you can write. Okay,
Yes.
correct. So you can again rewrite it as minus, it is just 1 by T del P. Can you write it?
Yes, and this is beta.
No, wait. Don't. Now we can compare, right? But n is not there. Why
Yes.
n is not there? Because in macroscopic case, always n is constant. We don't put it additionally, but n is there. In macroscopic, our classical thermodynamics, generally n is always constant.
Yes.
So that's it. So if you compare, this term is same. So from here you can directly write that beta proportional to 1 by t. Okay.
Yes.
Because instead of 1 by t, it may be some ct, then also it's true.
Yes.
If it is ct, then also it's true, na? So that's why it's proportional, not equal. So, and let's say there is a equality constant, proportional constant, that is k. So let's say that constant is 1 by k, then you can write it 1 by kt. So this is our beta.
KBT.
Now it's kt. You still don't know that k is actually kb. That you still don't know. How you can know that? When you calculate cv or cp, then you will see, okay, that is that this k is actually kb. From this analysis, what we have done so far in last 30 minutes, it's evident that beta is related to t, inversely proportional. But it's not
Yes.
sure that it is k, that proportionality constant is 1 by k. That you don't know. That you don't know. For that, you have to compare with the other things as well. Pressure, sorry, CV. From CV you can calculate, because CV is the only measurable quantity you know. Okay, so I think up to this it's clear, right? So now we'll calculate the various properties
Yes.
and uh, uh, term by term. First internal energy, then pressure, then we'll calculate Helmholtz free energy, free energy, these things. And if time permits, then we'll calculate also the entropy. Otherwise, entropy will calculate in the next class. But let us start. Just come in. So, let So we will calculate the rest of internal energies, rest of properties first. These things we have calculated last time, right? If I remember correctly.
Yes.
But it's okay. We should do it. E average, correct? Or
Yes.
Q average, whatever you want. So it is okay. This is capital P, J, probability. Small p is the pressure, capital P is the probability. This is our E average. So now, what is del Q, del beta in V? Can you write it?
Yes.
Okay. So what is now then the E average? Just denominator is 1 by Q, Q only. The numerator is now we can write it as del Q, del beta NP.
Yes.
So what that means this is this. So yes, this you can write. But this is one form. Another form is there. Just use KT instead of beta. That you can also do. So it will be now
Yes.
if you do it. So it is KT,
Minus KBT.
not it is 1 by Q. Sorry, 1 by Q is there. Then it is like this. Okay. Or from
Yes.
this equation also you can do it directly. From this equation also you can do it. Better to do that. So then it will be just the minus dln, so it is minus dlnq nv. So how you can solve it? It is correct.
Yes.
Okay. Can you do that?
Yes.
It is 1 by k times minus
1 by T
kt
square.
square. So it is oh one minus sign is there already. That will. So it
KT
is
square.
kt square. So this is our internal energy. So Internal energy has three forms. First one is just this one.
Del ln minus del ln q del beta.
No, first one is this one. Okay.
Yes.
In last course, I think pressure I did not do. You just do the pressure and just evaluate. Then I will do. Do it by your hand.
Okay.
It is easy. Nothing. I will give you 4 minutes. Good. Okay, so do it. You have 3 minutes. It was disconnected, right?
Yes.
Okay. Just my recording is going on. Okay, so have you done it?
I am doing.
Okay.
Minus kt del ln q del v.
Just check it. Minus will not be there.
No minus was there. Sorry.
Yes. So let me do it now. Yes, correct. This minus plus you have to be very much careful. Otherwise, these things will. Okay, so P. So Pj, capital Pj. Capital Pj is a probability. Okay.
Probability.
Ah, what was Pj? Minus del Ej del P. And it is e to the power minus beta Ej divided by Q.
Q. Sum over e to the power minus beta ij.
Ah, that's all. So what you can write now? Now just here del Ej is there, del Ej del V is there. So just now Q is sum over J e to the power minus beta Ej. So what will be del Q del V? Obviously n and beta is constant. So then it is e to the power J,
minus beta e to the power minus beta ej
yes, and e to the power Ej
del ej del.
n and T. So this is not our numerator, beta is only there. So what we can do, so can do we can multiply beta in numerator and denominator both as well. So it is Q, right? Q is Q, beta Q. Okay. So now the this part is written as can be written as 1 by beta Q del Q del V in beta. Okay, I think it's correct.
Yes.
Any minus sign will be there? No, it's correct. So it's equals to
Minus
just
minus plus
1 by beta dln q del v n beta,
yet constant in beta.
which is kt. So this is our pressure, average pressure. Okay, next one. Next one is our Helmholtz free energy. So you know Helmholtz free energy A equal to U minus or A E minus Ts.
2 minus ts.
Okay, for this you have to calculate the S entropy. That is not trivial. That is not trivial. Okay, but today there is not sufficient time to calculate the entropy that we'll calculate next day. But today just you assume what is entropy. This entropy average will be entropy will look in detail. This is our entropy. This
Yes.
will do. This will calculate in next class. So if this is our entropy, then we now calculate our Helmholtz free energy. So we have to calculate A average. So that will be E average minus T
Minus ts average.
exactly. So E average we have calculated. What was that? K T square dln q dt
Del t.
ln v. And now what will be Ts? Just kbt.
kbt lnq minus e average.
Okay, for timing we are not using kb. K.
kt lnq minus e average.
Okay. So E average. This was already direct. So from canonical ensemble, you can directly calculate the Helmholtz free energy. Just you have to take logarithm of ln of that partition function and just multiply it with kt. It is our Helmholtz average of Helmholtz free energy. Now, from these equations, what you can confirmly say, what you can conclude from this equation.
Helmholtz free energy is function of T and volume.
That is okay. Q is function of N, V, T, beta, so everything. T is also in the prefactor as well. What else you can see? Just see, this is Helmholtz free energy, not change. It is the absolute
Yes,
value.
absolute value of Helmholtz free energy.
Yes, so it should be positive. It can't be negative, right?
Yes,
That means KT is not a negative quantity. So LNQ
yes. So
should be
LNQ is
negative.
negative.
Q should
Q
be
is less than 1.
less than 1. Okay. So LNQ is actually negative,
Yes,
I think. So then you can ask, then what about this? Here LNQ, if it is negative, but it is not direct LNQ, it is a derivative of LNQ. So it can be positive, negative, anything. Okay.
yes,
And here also you see it is not direct LNQ, it is just derivative. So LNQ negative does not mean that its derivative is also negative. No. Okay.
yes,
Here from here you can conclusively say that yes, this is LNQ and this must be negative so that the average internal average Helmholtz free energy can be positive. Okay. Next is our enthalpy. That's why this Helmholtz free energy is probably called canonical equivalent something because it's directly linked with the canonical partition function.
canonical equivalent.
I forget the exact terminology, but it is something canonical like that.
It is the
But
quantity that
means
can be directly
thermodynamic
measured from canonical ensemble.
uh, canonical equivalent thermodynamical property, something like that. Thermodynamic equivalent of canonical ensemble, something like that is called actually. But you can understand the logic, right?
Yes,
Okay. Next is the Gibbs free
enthalpy
energy. Enthalpy is E plus
E plus PV.
so H average will be E average plus P average and V average is V. V is constant, so V is okay. So E average was our KT square DLNQ DTNV and P average was this. So KBTV.
KT del LNQ del V.
So you can write it.
Del LNQ del LNT del LNQ del LNQ.
Okay.
Yes,
Hmm. So this is our Helmholtz free energy is correct. And last one is what Gibbs free energy. So this is our enthalpy, sorry. And last one is our Gibbs free energy. H minus.
H minus TS.
So H is this and TS is this one. So okay, let me write it. KTLNQ
Minus E average.
hmm.
First term will cancel.
Exactly. It is KT, take common. These forms are not very straightforward, complicated form. This. Okay.
Yes.
Properties. We have left that
Can I prove G equal to A plus PV?
G equal to A plus PV. Check it. Check it. Check it. Oh, it's clear, right? See here. It is A. It is A. KTQ. This is A. And this part is P. And this is B.
Yes.
Right? Yes. It's clear. Everything is consistent. Don't worry. Yeah. Okay. Okay. So, but we did not calculate the entropy till now. Entropy will calculate. But today we'll do the last part of this canonical ensemble, that is a fluctuation. So this fluctuation part we can do today. Then we'll, if let's see if you wish, then we can do the grand canonical one. Otherwise, we'll see what we can do later. Okay, but today we'll solve the fluctuation part, and this fluctuation we had already discussed. This is our standard deviation, right? Standard deviation.
Yes.
This is our average, and if you make this and then again average it, then what is this is called our deviation, correct? This is called deviation.
Yes.
This is our deviation square.
Variance.
Okay, deviation square, and this is deviation square average. Average of deviation square. This is variance. Just for you remember, if x is a random variable, then x average. This is average. This is x square average, and variance of x is called x square average minus x average square. So what you can write it? You can write it as x minus this, right?
Yes.
So this is that. So this is variance. So this is variance, and variance was standard deviation square. Okay, we have to calculate this. E average minus E square. E average, you know. So how you can do it?
Yes.
So what you can write it from here, that E square is basically this one. Same thing.
Yes.
This part you know. E average you know. But E square average you don't know. That's why.
Yes.
Easy. What is E square average? It is just
Sum over
beta j,
square j pj.
beta ej divided by q.
Q.
Yes. Okay. This you have to calculate. So how you can calculate that? These things you have to calculate. So hmm, we need a trick. Okay, this is a tricky part. U is there. So just go. We can write it. Just see whether you can write it or not. Can you write it?
Yes.
Yes. If this is true, this is also true. Nothing.
Yes.
And this is
E average.
times Q. Okay.
Yes.
Correct.
Yes.
And this is you can write it.
Yes.
So so from here what you can do next, you can write it as minus E average. It is eventually KT square minus sign not there DL and Q dt. This you know.
Yes.
You can do it just beta equal to 1 by KT. If you put, then you can get it. And here also it is KT square daily delta. Constant is NPL. Okay, correct.
Yes.
And this part is called E average.
Yes. E average.
And this part is daily del T. What is this? CV.
CV.
Yes. N is constant now for 1. So it is E square plus KT square CV. So it was our E square average. So it's clear that E square average minus E average square is KT square.
KT square CV.
Correct? And this is our
Yes.
eventually sigma E square standard deviation square variance. So what will be our standard deviation? Just
Root of KT square CV.
exactly. But you know, we have discussed our relative fluctuation is more interested term, right? Instead of fluctuation. So this is our
Which is more important instead of fluctuation?
relative fluctuation. Fluctuation means standard deviation divided by mean. Then only
Yes.
we will get idea. Na? Let's say your mean is 20 and your fluctuation is 2. Then it's okay. But your mean is 0.5 and fluctuation is 2. Then fluctuation is same both cases, but mean are different. Na? So relative fluctuation is more
Yes.
and daily. So this is now for ideal gas, consider ideal gas, a specific system ideal gas. For ideal gas, you know the internal energy is of the order of kVt, right?
Yes.
Average internal energy of the order of kVt. We have already calculated using the equipartition. We know of the order of nkVt or RT. nkV is R.
Yes.
RT is 3 by 2 RT, 5 by 2 RT. These things we have calculated. So CBM will also order of that same thing.
Yes.
kV. So if that is the case, then you see the denominator and the numerator, both numerator is of the order of, this is of the order of
Total 1 by T.
nkb to the power half, and this is order of nkbt to the power 1. So it is just 1 by n to the power half. So it is actually order of n to the power minus half.
1 by k to the power half.
K is constant.
T to the power T temperature.
Oh, sorry. No. N kBT. Okay. Ah,
Yes,
okay. This. Now it's correct, right?
but CV is of n kb, not the
No. N
T
kBT. Its derivative with respect to 1 minute.
temperature. Derivative with respect to
One
temperature.
minute. Oh, correct. You are correct. But here it is T square.
Yes,
Yes.
internal energy this kT squares.
Okay. So you see, this is our order of fluctuation. So it's around 10 to the power minus 12. So you see, fluctuation is negligible. This is our RT.
Yes,
The average is RT, and around DRT 10 to the power minus 12 is fluctuation. So it's essentially negligible. That's why in our room temperature, there is no fluctuation. We can ignore the fluctuation. It tends to zero
yes.
eventually. Correct.
In how many temperature I can say it is relevant the fluctuation is.
The temperature must be tends to zero, very low temperature. But for then also for canonical ensemble, in this case, this fluctuation is anyway. For other type of distribution, you have to take this. Discussed in first class. There are various type of distribution, binomial distribution, Gaussian distribution, Gaussian distribution. This type of there are various type of distribution where this fluctuation plays a very important role. But obviously, if the system size is small, means the an is very small. You see, here the an is 10 to the power 23. You are saying 1 mole of n, right? But let's say you have only 10 molecules, then the fluctuation is not negligible.
Yes,
So that system size is very important. That's why in our quantum mechanical system, we have to consider the fluctuation. We can't ignore fluctuation part there. But here essentially we can ignore. Okay, so
yes.
it's okay, but in just entropy part is left that we will do in the next class, and then we'll see what we can do. We can do grand canonical, not in detail, but just overview we can have. Then we can see what's going on in the course. Then I will see. Then according to the course, again we will discuss. Okay. So
Okay.
is there any doubt from today's class? Let me stop sharing first. So
In today's week, the fluctuation part is discussed. So the problem will be based on this. So
fluctuation.
how I will solve this problem from
Okay.
which source?
Do you have any problems regarding fluctuations? Means numerical problems, I'm saying.
Yes.
Okay, then you can send me. We will discuss in the next class. And from
Okay. And
assignment also, I will see the problems. What the problem is given. That we will also do. First, we'll do the entropy part, and then we will do the rest of the things.
okay. And sir saying that the Castellan book is well written. So please send the book
Castellan, you don't have.
that is deleted from my WhatsApp
Oh, okay. Yes, I will send.
and the notes also, please.
This note. This note I
No,
uploaded in.
the quantum mechanics part.
Oh, okay. That I have shared you. That I will again have to share again, right?
Yes.
Okay, I will share it. And this note I will upload it in the spreadsheet, and from where I am doing this, that note I will share after this course.
Okay.
Okay. Okay, so thank you for joining again
Thank you.
next Sunday.